Hi everyone. We only have a new chapter and some new topics today. So we're going to get into random variables and probability distributions. And what I want to do is I want to start off with a couple of examples. Now, with a lot of times, we talked about probability experiments, and a lot of times we're actually more interested in not so much the outcomes or a set of outcomes, but a number that's associated with an outcome. Okay? And well, let me just start with this example. So a fair coin is tossed 3 times. Fair meaning there's no bias involved. And we're going to let X be the number of heads. Now, X, of course, depends on the outcome, right? And what I've listed here are all the possible outcomes of tossing a fair coin 3 times, right? So we can see that in this first case, there's no heads. So in this case, X would be 0. Okay. In these next 3 outcomes, we can see there's exactly 1 head, right? So in this, we see that X is equal to 1. And in these next 3 outcomes, we have exactly 2 heads. So for these outcomes, X equals 2. And then in this last outcome, we have 3 heads. So in this case, X is 3. Okay? And those are all the possibilities for X, right? So now we can talk about not so much the probability of a set of these outcomes, but we can probability of what X is equal to. And we can see that the probability that X equals 0, well, there are 8 outcomes, but only one of those outcomes has X equals 0. So the probability that X equals 0 is 1/8. The probability that X equals 1, well, there are 3 ways that can happen. 3 out of 8. So the probability that X equals 1 is 3/8. Similarly, there are 3 ways that X could equal 2. So the probability that X equals 2 is 3/8. And we said there's only one way that X could equal 3. So the probability that X equals 3 is 1/8. All right. Now, what we've actually done here is we've actually correspond exactly one value of X corresponds to each outcome of the sample space. So without actually defining it, we've actually defined like a function going from the sample space to the set of all the possible numbers, which we're basically assigning a value to each of these outcomes, right? And then we've computed the probability that this X is equal to one of those values. Now, let's look at another example. Here, it might help if I get the right page. So we have a 10-foot rope is randomly cut into 2 parts, okay? And then we're going to let X be the length of a smaller piece of rope, So if you cut this in 2 pieces, the longest that the shortest piece of rope could be would be 5, right? So we're talking about, so X is going to be some number between 0 and 5, basically. So here's X, and then here is 5. Okay, so this is the piece of rope that we have, and and we can see it has to be at least 0, and the most it could be is 5. So we can see that X is going to be greater than 0, and we'll say less than or equal to 5. We'll allow X to be equal to 5. All right. Now, of course, X could be an whole number. It could be 1, 2, 3, 4, 5, but it could also be lots of other numbers. X could be like 2.7 or 3.865. So there are lots of possibilities in this case, unlike the other case. So let's see what would be when we talk about the probability that X equals a particular number. There's a little bit of a problem here because let's say if we want to find the probability that x maybe is equal to, let's say 2, okay? Well, we're not really saying, it wouldn't make any sense to say the probability would be 1 out of 5, okay? Because really we're talking about, okay, so here's our spectrum of possible values of x, and here's 2. And it really is just like a point on this number line, right? So this is very, very small. Another way to think about this, if you were to pick a point, a random point on this interval, the probability that that point is exactly 2 is pretty small. Okay, in fact, we would say that the probability that x equals 2 is almost 0. Now, it doesn't make a whole, maybe it doesn't make a whole lot of sense. We don't want to say it's equal to 0 because that would mean there's no possibility it could happen. But it would be infinitesimal. What makes a little more sense is to talk about what's the probability, let's say, that x is between 1 and 2. Okay. Then if we talk about that, so here's 0 and here's 5. Here's 1, here's 2, here's 3, here's 4, and 5. So here's 1 and 2. And basically now we're talking about the probability that x is in this range. And we can see that this interval is about 1/5 of this whole interval here. So we could say the probability that x is in this range is actually 1 out of 5. So we can say that this is equal to 1 out of 5. If we wanted to find the probability, let's say that x is greater than 0 and less than or equal to, let's say, 3.2, okay, well, we're in this situation here. Here's 0, here's 5, and here's 3.2. And we're talking about the probability that that x is in this interval. So we can say, okay, well, the ratio of this shaded interval to the whole thing is about 3.2 to 5. So this would be basically 3.2 over 5. Okay, and notice that there is a big difference in these two examples. Because in this first example, x is here. In this example, there were only finitely many possibilities of x. So it's pretty easy to compute the probability that x is equal to a certain number. Okay. Now we can also, like obviously in this case, we could also talk about the probability that x is, let's say that x is between 1 and 2. We can still talk about that, but in this case, that probability would just be the probability that x equals 1 plus the probability that x equals 2, which would be 3/8 plus 3/8, which would be 6/8, right? But it was not there's, but we can't here in this case. We can't really talk about the probability that x equals a single value. We can basically talk about the probability that x is in a certain interval. And this is the difference between, we talk about discrete random variables. In this first example, x is an example of a discrete random variable versus here, in example 2, where it's we're talking about what we call a continuous random variable. And let me just give you the actual definitions here on page 3. A random variable, we say a random variable x represents a numerical value associated with each outcome of a probability experiment. And then a discrete random variable has finitely or infinitely, or rather finitely or countably many possible values. A continuous random variable is a random variable that has uncountably many possible values. So by what countably, when we talk about countably, what's the difference between finitely and countably? If it's countably, it could be infinitely many, but they can be counted. as an example, if we were to talk about, if x could be, just any positive integer, like 1, 2, 3, 4, 5, and so on, all the way up to infinity, that would be infinite, but it would be countable. Whereas with a continuous random variable, it could be, it turns out there are uncountably many numbers out there. If you talk about a finite segment of the real number line, there's you're including not just integer values, but all possible values. Like, let's say, all numbers, let's say between 1 and 5 would be not just 1, 2, 3, 4, and 5, but all the other fractional numbers. Okay, so that's what we talk about when we talk about continuous random variable. Okay, so just give you some examples of difference. If we talk about the number of cars in a university parking lot, that would be an example of a discrete random variable, because we could have the number of cars has to be a whole number. If we talk about the length of time it takes to complete an exam, that would be an example of a continuous random variable, because you could talk about 1 minute or 2 minutes, but you could also talk about 1.35 minutes or 1.6237 minutes. Okay, so that would be continuous. The volume of blood drawn from a blood test, that would also be continuous. The number of tornadoes in the month of May in Oklahoma, that would be an example of a discrete random variable, because that number has to be an integer, a whole number. Number of texts that a student sends in one day, that would be discrete. And the amount of snowfall in inches in a certain city during a certain winter, that would be continuous, because it's length. Okay. All right. So those are examples of the difference between discrete random variables and continuous random variables. So now we're going to, in the next video, we're going to focus on discrete random variables and the wonderful stuff we can do with that. So see you next time.